Chapter 4, Linear Algebra Basics. Real-world systems can be approximated or represented as a system of linear equations, ax equals b. Here, b is the source vector and x is the solution. In this chapter, we'll study topics in linear algebra basics, including elementary row operations, row deduction algorithm, linear independence, and invertible matrices. In the last chapter, we studied programming with calculators. Calculus and linear algebra are two major topics you have to understand well if you want to be a good programmer. Okay, let's go to section 4.1, Solutions of Linear Systems. A linear equation in the variables x1 to xn is an equation in this form. Here, b and the coefficients a1 to an are numbers. They can be real or complex valued. A system of linear equations, or simply a linear system, is a collection of one or more linear equations involving the same variables. Here, the left-hand side is a system of two linear equations with two variables, x1 and x2. And right side is a linear system of three equations with three variables, x, y, z. Solution of a system is a list of numbers, s1 to sn. That makes each equation a truth statement. Once x1 to xn are replaced by the list of numbers, then every equation will be true. In the case, the list of numbers becomes a solution. The solution set is a set of all possible solutions of the linear system. And two linear systems are equivalent if they have the same solution set. For example, this system and this system, this one is made with this operation. The first equation is replaced by first equation minus second equation. Here, second equation is subtracted so that 2x1 minus 4x2, and that will become minus 2. So that is this the equation, and this one is the same as earlier. These two systems will have the same solution. So we say these two linear systems are equivalent. Okay. Linear systems may have no solution, exactly one solution, infinitely many solutions. When it has no solution, then we say the system is inconsistent. Once it has at least one solution, so the either unique solution or infinitely many solutions, then the system is consistent. Here we consider the case of two equations in two unknowns. Okay. For this system, we may write this one in a more convenient form. So y equal, by moving minus x to the other side, we can have that is x plus 1. Second equation will become y equal x plus 3. Now, if we draw graphs of each equations, then one is this one, and another one is that one. There's one here, and there's 3. The slope is 1 for both equations, and so that the graph never meet each other, so there's no solution for this system. And the solution will be the intersection of the 2 lines, but these 2 lines are not meeting each other, so that there's no solution. How about this one? If we write this one in a convoluted form, then y equal, that is minus x plus 1 from the first one. From second one, y equal x minus 2. One is slope minus 1. The other one is slope 1. So that one is minus x plus 1 and x minus 2. It is passing that way, so that the point, the intersection, is the solution. It has unique solution. Now, here, if we multiply 2 to the first equation, then we can get second one. That means that these 2 equations are essentially the same. So this one, each one is making a line so that the graphs are identical. That means that 2 graphs are meeting in every point, and so that it has infinitely many solutions. Here we have 3 systems. One has no solution, one has a unique solution, and the last one has infinitely many solutions. Okay. Now we'll consider how to solve a linear system conveniently and efficiently. Let's begin with this simple system of 2 linear equations. Now, for this system, we may try to express it in metric form. So we collect the coefficients, so -2, 3, 1, and 2, so that it becomes the coefficients metric for the system. And then x1, x2 are the variables, and that is the right-hand side. So that is a metric form, metric equation. Now, from this one, we may try to get essential information of the system, this coefficient metric and right side. We put together to make the augmented metric. So metric and right side. To indicate it is an augmented metric, sometimes we are putting vertical line or vertical dashed line. And either way, we can indicate this last column is from right side. Or sometimes we know the vertical line. It's okay. If we understand it, that's fine. Now this one has essential information, every information from the system. Now let's try to solve the problem. Okay, this is the system of linear equations. Now that is corresponding metric form having essential information -3, -1, 1, 2, 4 we have here. Now if we interchange the rows, then from here we can get it. Now similarly, we try to interchange the row of the coefficients, the information, then we can get that one. Now this metric is representing this system 1, 2, 4, -2, 3, -1, right? Okay. Here, as the beginning step of solving the problem, Now we will try to eliminate this one. That can be done if we replace the second row by second row plus twice of the first row. Okay, first equation twice is added to the second equation, then it'll become 0. So twice added, so it is 0, and twice added, it is 7x2, twice added, so it becomes 7. Exactly same way, we can apply in the operation. So twice added, it'll become 0. Twice added, that's 7. Twice added, again 7. And you may compare the left-hand side and right side. The right side is representing the system of equations. Right? Now, scaling for the second equation divided by 7. Now that is corresponding in metric form here. Just a row, the second row is divided by 7 from here. So we can get this one. Now we can eliminate this one by subtracting twice of this second equation. Then it will be 0. 2 subtracted, so it becomes 2. Now the same operation can be applied here. So twice subtraction, that will become 0. Now that will become 2. So this final metric form is representing this one. So here in the last step, the solution is 2 and 1. And from this one, now this is identity metric, and right side, that is the solution. Okay, we go back to the top. We start with an augmented metric. So it is the augmented metric of the system. And start with this one. Now we apply the elementary row operations, interchange, replacement, scaling, again replacement, so that this portion is changed into the identity, and now this extra column becomes the solution. Okay. Okay. Here we collected these operations, 3 elementary row operations. The first one is replacement. Replace one row by the sum of itself and multiple of another row. Ith row is replaced by ith row plus the k times of jth row. That is replacement. And interchange is changing 2 rows, ith row and jth row. And scaling, and we can multiply a row by a non-zero constant k. So we can get the scaling. We used these operations. These are 3 elementary row operations. You will use this one again through the whole scope of linear algebra. And this will be the major weapon for solving linear algebra problems by hand. 2 matrices are row equivalent if there is a sequence of elementary row operations that transforms one metric to the other. For example, in this computation, this metric is row equivalent to the identity metric, because by using these elementary row operations, the sequence of these elementary row operations, we reach at here the identity metric. Okay, and matriciation AX equals B. fundamental idea in linear algebra is to view a linear combination of vectors as a product of a metric and a vector. Okay, here A is an n by n metric and having n columns, A1 to AN. Then the product of A and X, it is denoted by AX, is the linear combination of columns of A using the corresponding entries of X as weights. Here AX, A is written with the columns, and there's X. Then it can be written in this way: x1 a1 plus x2 a2, and then the last term is xn an. So this linear combination of these vectors and also the product of the AX, once A is the collection of the vectors, and these are the same. So we can view a linear combination of vectors as a product of metric and a vector. Of course, the metric is collection of the vectors. A metric equation is of the form AX equals B, where B is a column vector of size M. Okay. Now, for this system, or is a metric equation or vector equation, the solution is -3 and 2. Now, once it is written in this way, we usually say this is the system of linear equations. Now, that one, once it is written in this metric form, then it's called a metric equation. And once it is written along with the columns, so vectors, then it is called a vector equation. Okay, but no matter how it is expressed, this original system is same as this vector equation, and also same as this. Okay, that is metric equation, sorry, and that is vector equation. They are the same. So we have a theorem. A is n by n metric with A1 to AN columns, and B is a vector in Rm. Then the metric equation has the same solution set as the vector equation. So along with the columns of A, we can write this equation into this vector equation, and which in turn has the same solution set as the system with the augmented metric. So that is from A, metric A, and that is from right side. So the solutions from each one must be the same. Okay. In linear algebra, we have two fundamental questions, and for solving linear systems. And first one is existence. You may ask, is the system consistent, or does at least one solution exist? Such a question is about existence. And uniqueness is related with the only one solution. So if a solution exists, is it the only one? That means, is the solution unique? You may ask such questions. in many cases, once the system has no solution or infinitely many solutions, then you will spend a much more hard time to get reasonable approximations. So once the system has unique solution, then you can solve the problem relatively easier. So that such question is very fundamental in many applications. Sometimes existence and uniqueness is not guaranteed, then you cannot get the solution. So it is very crucial for some tasks in linear algebra. Determine the values of h such that the given system is a consistent linear system. That means that we try to find the h such that the system has at least one solution. Okay. Now, we already know that for the linear system, we can write in this way, in metric equation or vector equation, or in augmented metric. So we'll try the augmented metric. Okay, we collect here essential information, and 1 quotient and h, and 2 minus n is from the quotients metric, and right hand side -5 and 6. If it has at least one solution, then original system will have the same solutions. Okay, from here, okay, let's try to apply elementary row operations. Okay, eliminate this one by subtracting twice of the first row, 1h -5, and that is 0, and there is a -8 and -2h, right? Twice subtracted, and this one will be 16, right? Okay. Now here, okay, if this is 0, for example, that is 0, that means that there is 0x plus 0y equal 16. Left hand side is 0 and right side is 16 is impossible. If it is non-zero, then we can scale and we can get the solution. So here the requirement is -8 minus 2h must not be 0, right? That's the requirement. Then for h, which satisfies this equation, and here we can scale and we can decide y value, and again here by eliminating this one we can get here x value. So h is any value except this one, so that that is h is now not -4. Okay, so h is not -4, then it has solution, but the solution is unique, right? Okay. Okay, that's the end of section 4.1. Thank you.